All right, good morning. I hope you're doing well. And I'm getting this done on Saturday morning and excited to get this idea across to you. I hope I can help you get mastery of this. This is super important but easy idea. So if you can get this, then it's going to really help you with a whole bunch of questions that they can ask you. Um, Hopefully you've already done the one where we looked at the force of attraction between any two objects, this equation right here. Force of attraction due to gravity for any two objects. Put in the mass of the two objects, put in the distance between their centers, you can calculate the force of attraction. That's very useful. But there's something that's even more useful, and that is this concept of G. Now, I've been using G all year already, and I've been putting G on the board and treating it like, oh, that's acceleration due to gravity. And, you all know it's 9.8 meters per second, and you've thought of that as being G, but I've been oversimplifying that the whole time, okay? And now we're going to talk about it in a much more realistic and powerful way. And we're going to change the units of it as well. Because I want you to think about something like this coffee cup sitting on my hand right now. This coffee cup that's sitting on my hand is not accelerating downward at 9.8. It's not moving at all. The net forces have canceled on it. So the 9.8, what am I using it for? It's still important, but what am I using it for? And so this new idea about what 9 is, or what G, small g is the gravity field. And when we say gravity field, we have a very specific set of units in mind, and that is newtons per kilogram. So now when I say I have 9.8 newtons per kilogram of gravity field, what I'm saying is that I will get a gravity force because I'm in that gravity field that is dependent only on the mass of the object in the gravity field. So the gravity field, right, all around us on the surface of the Earth, and even if you go pretty high up, it's still around 9.8. You got to get way up by where the satellites are and stuff before it starts getting much less than 9. So it's this idea that gravity is a field, that when you have an object in it, there'll be a force that depends on the mass of the object. And so 9.8 is now newtons per kilogram, and it's still 9.8. But the idea is that if I have, say this cup actually weighs, 1 kilogram, then there'd be 9.8 newtons of gravity force acting on it. But if this is 100 times less, this little pencil, and so it's, say 10 grams or something, then the force of gravity on it would be 0.098, newtons. Or if you had 2 kilograms, then what would be the force of gravity on it? You'd say, 9.8 newtons per kilogram, and we have 2 kilograms. So 9.8 times 2, and you get your 19.6 newtons of force acting down on it. So the idea is that force depends on the mass when you're in a gravity field. And this is the force. This is not the acceleration. So when I say, this is 1 kilogram, and so the force is 9.8, I'm not saying I should get 9.8 meters per second squared. I shouldn't, because my hand is pushing up at the same force, and there's no net force. Even if it's moving at a constant speed, there's no net force. There's no acceleration. And so we can't say that there's 9.8 meters per second squared. That's silly. But we can say that there's still in a gravity field, and that it has 9.8 newtons per kilogram, of force in the gravity field acting on that object due to gravity. And that's what small g is, super powerful. The other thing about little g is you can figure it out for different locations. What if you are in orbit? Clearly, there's still gravity out there in orbit because those satellites are going in circles. The forces are pushing it towards the center of the circle as it goes around in a circle. And so that is being caused by gravity. So there's still a gravity field way out there. People often have that mistake. They think, I thought there was no gravity when you're in orbit. No, there is there still is a gravity field. It's close to 9.8. Actually, it's not that much less, but it's all being used to make you go in a circle. So that's why you're in what's called free fall. Free fall is not the same thing as no gravity. There's still plenty of gravity. Anyway, the idea of a gravity field, right? The idea of a gravity field that always points towards the center of the object is why we were using R in this equation. In the last screencast, I was like, we should use D. Why do they have R? But now we see why they have R. Because if you're on the surface of any planet and you ask yourself, how far are you from the center of the planet in terms of distance? That is R of the planet. Like, here's a planet from the center of the planet out to where you're standing. The distance from your point mass to the point mass down there, that distance is R. So like if this was the mass of the Earth and this was the mass of you, and you put in R for the radius of the Earth, you could calculate the force of attraction of the Earth and you. And the Earth is pulling on you and you're pulling on the Earth with that same attractive force. That's a lot of work to do every time, and it's annoying. So instead, we do the math to figure out the gravity field. And so that's where this equation comes from. So for any planet, we can figure out the value of the gravity field on the surface of the planet by using this equation down here. And so G is the same capital G we used before, 6.67 times 10 to the negative 11. You know, M is now the mass of just the planet. There's not two M's here, right? There's just one. And that's the mass of the planet, where you're curious what the gravity field by that planet is. And then R is the radius of the planet, because that's the location where the gravity field is. I think this could still be a D. It'd be okay. Because if here's the planet and you want to know, like, okay, if I go a few diameters of Earths away, like I'm way over here, you know, 3 Earths away out in space, what's the gravity field out there? And you could still calculate the gravity field out there because you'd do this same math. You'd have capital G, you'd have the mass of the planet. For R, you'd go from the center of the planet out to the location that you're curious about the gravity field. And you can calculate the gravity field at any distance from the center of the planet. And that's what this equation is about. But the reason, again, they're using R is because they're talking about at the surface of the planet. And at the surface of the planet, clearly the distance between the planet and you, because it's the center of the planet to the center of you, that's going to be about the radius of the planet. Okay, so I want to derive this equation right here and then plug and chug for the Earth itself. So we have data for the Earth. Here's the mass of the Earth. Here's the radius of the Earth. Wrong units, got to be in meters. And we're going to plug and chug that in with G to get small g. So be careful. This is the universal gravity constant, capital G, not to be confused with gravity field, small g. By the way, gravity field, little g, is a vector. And so it can cancel each other, and we have to do triangles to solve them, and all of the things we did with vectors we can do with little g, which we'll look at a problem here in a minute on a different problem of the day. But in any case, very straightforward little derivation, because if you take and solve this F, you get, say, okay, so let's say the force of gravity in a gravity field, what would that be? Oh, that would be F equals mg, because the m comes over here. So if F equals mg is the force in a gravity field, which it is, that's the definition of a gravity field. This is the definition of a gravity field. And then Newton's universal law of gravity is still true, like this is true. So this is the definition of a gravity field. And then this is, you know, Newton's law of gravity. So we just use both of them by solving for F here and then putting this F equal to this F. And let's look what happens. Very straightforward, very easy. Okay, so we say that the force of gravity is given by Gmm over r squared. Like that's what we did in the first problem of the day. We understand that's force of gravity. Then over here, from the definition of gravity field, little g is gravity field. And by the definition of gravity field, we know that the force in a gravity field is equal to the mass times the gravity field, right? This is mass, this is gravity field. So yeah, this force of gravity is the same as this force of gravity, which means this equation is equal to this equation. And we notice that the mass of the object in question, the person or whatever is on the surface of the Earth, that gets canceled. And now we have the equation for the numerical value for the gravity field on the surface of a planet, where r is the radius of the planet in meters. Make sure you change it to meters. G is universal gravity constant. You can plug that number and store it in your calculator so you have to type it in all the time. Anyway, this is the mass of the Earth. Plug and chug those numbers through. You should get something close to 9.8 newtons per kilogram, which is where this 9.8 meters per second squared came from. But we should really stop calling it meters per second squared unless it's actually in free fall and accelerating at 9.8 meters per second squared. So from now on, we really should say newtons per kilogram now that we understand that concept. So lots of important ideas here, and we see that 9.8 comes out of the characteristics of the planet itself, the mass of the planet, the radius of the planet, and those are related to things like, what the density of the planet is. So different planets will have different accelerations due to gravity because they have different gravity fields, and we can calculate those different gravity fields for various planets in the solar system or in the universe at this point, and that's fun and useful. So hopefully that helped you understand these three equations and how they tie to each other and how we use them in a simple question such as showing that the gravity field on the surface of the Earth is indeed 9.8, as we already knew. So see you again soon.